In order to discuss how reactions occur, we'll need to look into something called collision theory. Collision theory allows us to understand how reactions occur. There are three factors that affect the course of any chemical reaction. Number one, the particles must collide or at least come in close contact with each other. If they're not near each other, they cannot react. Generally, if you have them in two different containers, they're not going to react. But if they're separated by a layer of oil or something like that, again, they may not be able to contact each other, in which case they will not react. The second factor that affects chemical reactions is that the particles must collide with enough energy to interact. These particles have a minimum kinetic energy. We call that the activation energy. It's how much energy they have to get in order to react with each other. So if they hit gently, there's no reaction. But if they bump into each other with enough force, there's an actual reaction. It's sort of like when you back up and you hit a car or something and there's no damage. That would have not enough energy to damage something. Whereas if you back up or hit somebody with enough force, you will see an interaction. Something happens to that car. It's similar to that. And the third factor states that the particles must collide with the correct orientation. In other words, they have to be facing the correct way. If two people try to shake hands and they're both facing to the north, obviously they can't shake hands because their hands will not come in collision with each other, which is where the interaction would occur. And so for these reactions to occur, each particle must be held in the correct position so that they can interact with each other. Now, sometimes we use something to hold it in that position. Other times it just happens by random chance. And now we're going to look at how the energy of a reaction changes over the course of the reaction. This diagram shows the potential energy that is present over the course of a reaction. So in this diagram, we're going to see that there are starting materials, and they have a certain amount of energy. We're going to have an activation energy that tells us how much energy it takes overall for this reaction to occur. Remember, we talked about the minimum energy required. And then we're going to look at the products at the end of the reaction. So this is given over time. There is no time on here, but we're just saying from the start to the end of the reaction. We have different terms for whether the change in energy is increasing or decreasing. So here we see a starting material at one level, and if we end up with a higher energy level for the products, we'll be calling that an endothermic reaction because energy was absorbed from the system and it's now stored in the products. On the other hand, we could have a different reaction where it goes up to the activation energy and then it drops down and it's below the original energy of the starting material, and the products have less energy than originally. That means they gave away some of their energy, and we call that an exothermic reaction. And now we'll look at a couple of specific examples. So in this first diagram, we can see that reactant is higher than product, so we know that this is an exothermic reaction. Now when we look at this, we're going to have an activation energy. That's how much energy it takes to get the reaction started. Maybe we have to add a little extra energy to something. An example of this might be when you're burning wood. So you have the wood, it has stored up energy, it has potential energy, and then we have to start it with a match or something to get it started. Once it gets started, now it releases a lot of energy, and you can feel the heat and see the light coming off of that fire. So we know that that is an exothermic reaction because it's giving off some energy. Notice though that it needed something to get it started. That was the activation energy. In the second potential energy diagram, we see that the product has more energy than the reactant did. We're going to see that it goes up in energy and it has an activation energy that is even higher, but when it comes back down, the product holds on to more of that energy. So we know that this is an endothermic reaction. An example of this might be like boiling an egg. To boil an egg, you have to heat it up, and then you can allow it to cool down, but that egg is holding on to that energy. It doesn't give off any energy afterwards. It doesn't give that away, and so it stays as an endothermic reaction because it has more energy stored as a boiled egg than it did as a natural form. And for this third example, we'll notice that the products are lower in energy than the reactants, so we can see that this is an exothermic reaction. It's giving off energy. But what's different about this one is it doesn't have that big hump in the top, so it doesn't have an activation energy. Because this doesn't have an activation energy, This reaction is spontaneous. That means it happens with no added energy. And so this reaction will occur as soon as those two chemicals come together, they start reacting. An example of this might be your baking soda and vinegar. When they come in contact with each other, as soon as they're in contact, you'll start to see those bubbles form and you'll see energy given off. And so that's an exothermic reaction, and it is spontaneous. There are no spontaneous endothermic reactions because they have to go up in energy and energy has to be added to them. So exothermic reactions can be spontaneous or not spontaneous. Example 1, wood burning, is an example of one that is not spontaneous because you had to add energy, light it with a match, do something to it to get it started. Once it started, then it gave off more energy. But in the case of baking soda and vinegar, we see that they react immediately upon contact, and that is a spontaneous reaction.